Hi everyone. Thought I'd start out today's video with a fun little math fact. If you take the number 82818079, hopefully you get the pattern 7, 8, all the way counting down to 1. Okay, that number by its that collection of numbers put together as a single number, that is a prime number. That is prime. Which, who cares? That sounds insignificant. What's the big deal? It's the only one I know of that form. Like if you take the number 1, that's not prime. We know that that's neither prime nor composite. If you take the number 2, 1, that's 7 times 3, that's not prime. If you take the number 3, 2, 1, that's not prime, obviously. Or not, maybe not obviously, but it's not prime. You can check and find a factor in 3, 2, 1, 4, 3, 2, 1, 5, 4, 3, 2, 1. All of those are composite numbers. But tack on enough digits until you get an 82 at to that digit, then finally that number is prime. And then if you keep going and tacking on more and more and more digits beyond 82, 83, 84, all of those are composite up to every number that a coworker of mine checked, because that's what math people do. We do this kind of stuff for fun. Kind of cool, fun little math fact. Wanted to share with you. Today we are covering section 5.4, Eigenvectors and linear transformations. Okay, so I'm going to show a picture in just a moment that I drew and is going to look beautiful. But let me write down kind of what our goal here is in this section, because we've been working with eigenvectors and eigenvalues for a few sections now. This is the last section we cover in chapter 5, and our goal in this section is to understand that equation A equals P D P inverse that we've seen now a couple times, which is in itself a factorization, right? P, D, and P inverse, those would be factors of the matrix A. If they multiply together to produce the matrix A, they are themselves factors of A. But to understand that equation as a statement about linear transformations. Linear transformations. Okay, so that's kind of how this textbook has been going. We get like a little bit of new information, and then we tie it into the concept of a linear transformation. Get a little bit of new information, tie it into the concept of a linear transformation. And that's what we're going to do here. Okay, so now let's take and make the big reveal here. Take a look at this picture. There's kind of a lot going on, so let's take a look at it. We've got, let's start with focusing on the top here. We have V is an n-dimensional vector space. Let me write that down. V is n-dimensional. And W is m-dimensional. W is an m-dimensional vector space. And we define T to be any linear transformation from V into W. So take a vector X, put it over there, right? So I take T takes some vector X and maps it into W, and in W we call it T of X. That's its image, the transformed vector. Now, if we want a matrix, say, associated with T, we can choose a basis B of Rn and a basis C of Rm for those two different vector spaces V and W, okay? And then introduce the concept of coordinate vectors. So now I'm dropping down into my XYZ plane, but not really XYZ. I'm dropping down into Rn, the coordinate vector X relative to basis B, and then we would have a coordinate vector of T of X relative to basis C. And then what we want, oops, I don't want to be on my highlighter right now. We want a connection between these two coordinate vectors. That coordinate vector and that coordinate vector. Okay, that's what we're trying to establish the connection between. So let me move my screen up a little bit here, and we're going to say let B equal some set of vectors. Let B, that basis, be a collection of n vectors, b1 through bn. And then if x has coordinates r1, b1, plus etc. through rn, bn. If the r's are the coordinates of x relative to basis b, then if that's how I write x as linear combination, I should say, then its coordinate vector relative to b looks like this, r1 through rn. There we go. Okay, so this is x as a linear combination of the basis vectors. This is how we write its coordinate vector. And then, t of x, if I transform that vector, that vector x is t of r1 b1 through rn bn, right? That's apply the transformation to that linear combination. Well, since it's a linear transformation, that would be r1 t of b1 plus etc. rn t of bn, right? I can apply the linear transformation through to each vector in the parentheses and then pull the scalar out. And again, that's because b/c, because t is linear. Now, where we go next is to say that since our mapping, the mapping from W to RM, that's that mapping downward, is also linear, I can write the coordinate vector for t of x relative to basis c as r1 t of b1 relative to c plus etc. rn t of bn relative to basis c. If I'm starting to lose you a little bit, I'll tie it all up in a nice little bow shortly, so bear with me. I know the notation, it's about to get even a little bit worse, but just for a minute. So then our next step is to say that our c coordinate vectors are in Rm. So that scribble that out. This can be written as a matrix equation. Okay, and again, the notation gets a little bit uglier for a minute. So our coordinate vector for t of x relative to the basis c is equal to matrix M times the coordinate vector x relative to basis b, where M is equal to this matrix here, t of b1 relative to c, etc., t of bn relative to c. Okay, right, one more thing, and then I'll kind of sum it up. M is called the matrix for t relative to bases b and c. M is called the matrix for t relative to bases b and c. Whoa, kind of intense there. Long story short, to make the matrix for your transformation M, you transform the basis vector and then write it in terms of the other basis. You transform each basis vector and write it in terms of the other basis. Okay, that's the best I can do for long story short, sum it up. That's what that matrix, the matrix of the transformation, comes from. And it allows us to take our x vector relative to the b basis and multiply it by some matrix to produce its transformed vector relative to the new basis. So that's kind of the essence of what's going on here. We'll start out with an example that's not super complicated, just to introduce you to the notation or reintroduce you to the notation, and also to just kind of take a look at the relationships without having to grind through too much work. So pause it if you need to read through it once, but we have two bases, b and c. We define a transformation from v into w. It's a linear transformation with this property, right? So we have transformed basis 1 vector in terms of c transformed basis 2 vector in terms of C. We already have that established relationship. That's a good thing, and it's what makes this problem, again, fairly direct and not a lot of work. So just to introduce the notation, if I have B basis vector in terms of C, then I can write that the T of B1 relative to basis C, I can just write it in this different notation as a coordinate, as a vector, 3, -2, 5, and T of B2 relative to C is 4, 7, -1. So because I'm given that established relationship, all I have to do to write down M is, well, just put those two vectors together in a single matrix. 3, -2, 5, and 4, 7, -1. Now, I won't always be given that, but in this case I was, and that's what allowed me just to, boom, write down the answer. Okay, but when I have T of B1 in terms of C, that allows me to write that. T of B2 in terms of C allows me to write that, which gets us right to our answer. Now, it is often the case where we have linear transformations from V into V, not V into W, right? So our bases basically aren't changing. That almost simplifies things a little bit. Problems can still get complicated, of course, but notation-wise, we call this the B matrix, the B matrix for T, and the notation looks slightly different. T of X, the coordinate vector of the transformed vector relative to B, is equal to capital T relative to B. So that's in place of the M from the previous kind of formula, times the coordinate vector X relative to B. So there's no need to change from B to C or anything like that. This is maybe slightly simpler notation than was initially introduced. An example using that notation, notice here we're going for our transformation P2 to P2, so that's from V to V. We're not changing vector spaces or anything like that. Okay, and here is our transformation. Let me highlight it. There it is. T of that polynomial, that second degree polynomial, equals the first degree polynomial on the right. And if you notice, from the left to the right, the A naught is gone. There's no A naught. The A1 has a variable next to it, and then on the right it doesn't. And then the A2t squared, when you look on the right side, is 2A2t. And that transformation is where it says calculus students will recognize T as the differentiation operator. Basically, we have defined a linear transformation that takes the derivative of a function, of a second degree polynomial. So this is doing linear algebra, well, doing calculus with linear algebra. For part A, it says find the B matrix for this transformation given our standard basis 1, t, t squared, and then verify that relationship is true in part B. Okay, and we'll start out with A. And in A, we take each of our basis vectors, 1, t, and t squared, and we apply the transformation. We transform them. All right. If I want to transform a basis vector of 1, that 1 there represents the A naught in the yellow highlighted transformation. On the right-hand side, do you see any A naughts? No, you don't. So T of 1 is equal to 0. There's no A naughts on the right-hand side. All right. Let's see if we can do this with the next one. Now, in T of t, if I apply the linear transformation on the basis vector t, here, the A1 is the coefficient of t. Okay, take a second, process that. A1 in the transformation formula up above is the 1 in front of the t. Okay, do you see any A1s on the right-hand side? Absolutely. Just that A1 at the beginning, so that T of t is equal to 1. Okay, again, take a second to process that. See if you can see where everything went. The 1 in front of t is A1, and it ends up right there by itself. All right, now let's see if we can do the last one. t of t squared. If I transform my third basis vector, t squared, the number in front of t squared, its coefficient is 1. That represents the a2 up above, this a2 right there. And if you look on the right-hand side, there's a 2a2t. So my transform basis vector is 2t. So what did we just do, by the way? If you take the derivative of 1, you get 0. If you take the derivative of t, you get 1. If you take the derivative of t squared, you get 2t, right? But we've done it with a formula instead of calculus. Okay, so now our next step is we get to jazz up the notation. We're going to say then the coordinate vector t of 1 relative to basis b is equal to the 0 vector, right? We're writing this 0 as a vector, that as a vector in P2 with 3 entries. Okay. Similarly, t of t relative to basis b, that is 1, 0, 0, right? The 1 here is the 1 here because it's a constant, so it gets that first entry. Then t of t squared relative to my basis b is 0, 2, 0. The 2 in front of the t to the first power is the 2 that's right there in my vector. And now that we have our transformed basis vectors, we can write our answer. The matrix for this transformation, the B matrix of our transformation, or we can call it M, is 0, 0, 0, 1, 0, 0, and 0, 2, 0. And that is our answer to part A. All right. Now, part B, where we have to verify that if you transform a polynomial, that this relationship holds. Basically, if we take a polynomial, we'll start with an arbitrary one, meaning with variables. So our polynomial is a0 plus a1t, that's a t, plus a2 t squared. Does that matrix M work correctly? I know the derivative of that, but do I get the same derivative if I do the matrix multiplication? Okay, so let me write this down. T of p, so my transformed polynomial relative to b, should be a1 plus 2a2t, again, relative to b, and that looks like a1, 2a2, and 0. That's what we should get. We know that. And if you check and write down your matrix M, 0, 0, 0, 1, 0, 0, 0, 2, 0, then times a0, a1, a2, and go through the row by column multiplication. Well, that row times column produces just a1. This row by column produces 2a2, and row 3 to that column gives us 0. Hey, we got the same answer in both cases. Good job, us. Okay, good. Now we come to our first theorem in this section, and it's Theorem 8. Theorem 8 says, if I have, or suppose that A equals PD P inverse, where D is a diagonal matrix, so here's where we bring it back to diagonalization. If B is a basis for Rm formed from the columns of P, then D is the B matrix for the transformation x to ax. Okay, D is the B matrix for that transformation. So it's the matrix of the transformation relative to the basis B. Okay, so we're going to go through a proof of this theorem because it's cool. It uses some good substitutions. So let's write our proof. All right, so we're going to say denote the columns of P. Denote the columns of P by B1 through Bn, so that our B basis, capital B, is equal to those vectors, B1 through Bn. Boom, there we go. Okay, so there's our start. And that allows us to write P equals B1 through Bn. So those are the columns of matrix P. Then P times the coordinate vector for x relative to b is equal to regular x. That's just our coordinate vector equation. X is equal to the P matrix times the coordinate vector of x. And we can also solve that for x, the coordinate vector, excuse me. It would be equal to P inverse times x. So I'm going to erase this, but think if I multiply by P inverse on the left to cancel out there, well, really to get the identity, that's where that next equation comes from. All right, now undo all that. There we go. So where do we go next? Now we're going to start a new line here. If t of x, our transformation, is equal to a times x for x in Rn, then now we're going to have a big, huge series of equalities with a reason for each one. Okay, then the T matrix for relative to B, the T matrix relative to B is equal to, ready, here's some ugly notation for a minute, T of B1 relative to B, etc., through T, oops, I forgot my one, T of Bn relative to B. Boom. So those are the entries of that matrix, and that is just by definition. That is that's what it looks like. That's how you make it. Okay. So then we make a substitution. That is equal to A times B1. Oops, that's a terrible bracket. A times B1 relative to B through A times Bn relative to B, okay? And that is because since T of x is equal to A times x, the transformation just says multiply A by the vector. All right, now we make a substitution. This gets good. Then P inverse times AB1. Now we change our coordinates. P inverse, AB1, excuse me. P inverse times A, B, N. Those are the entries of that matrix now, the columns of that matrix. And that's, we make a change. I'll show you where this came from. A change of coordinates. All right, and so where the heck did that come from? Let me move up a little bit here and highlight this equation here. Coordinate vectors of x relative to b are P inverse times x. So coordinate vector AB1 relative to basis B, right? Let me highlight even more. What's inside the brackets is multiplied by P inverse. What's inside the brackets here is multiplied by P inverse when I make my change of coordinates. So that's the substitution that we made there. All right, and this is where it gets really good because I know, front of parentheses there, because I know how matrix multiplication works, I can take and write this as P inverse, pull all those P inverses out of each column, times A, pull all those A's out of each column, times the matrix B1 through Bn. All right, and my reason for that is just matrix multiplication. I'll abbreviate that word, right? Because I know how multiplication works, I can factor those all out. And what is that set of vectors B1 through Bn? P inverse times A times P. That's what that matrix, where that matrix came from. Okay, and then our final line of the proof here, and kind of we draw our conclusion, since A is equal to P, A is equal to PD P inverse, then the matrix for this transformation is P inverse A P, which is equal to D, right? If you solve that for D, you get D equals P inverse AP. Cool. So that says ultimately that D is our man. D is our man. D is the matrix for our transformation. D does the same thing to that the A matrix does, but relative to a different basis. Now we get an example where we use that theorem from just a second ago, and we have a transformation that we defined from R2 to R2. T of x is equal to A times x. A is this matrix that we've actually seen before. It says find a basis for R2 with the property that the B matrix for T is a diagonal matrix. All right, so how do we do that? First thing I want to note from section 5.3, we have A is equal to P D P inverse, that given matrix A, with P equal to 1, 1, minus 1, minus 2, and D is equal to 5, 0, 0, 3. Okay, so there is our diagonal matrix. And the columns of P are eigenvectors of A, also the entries along the diagonal of D are the eigenvalues. So then we'll say by theorem 8, D, that D matrix, D is the B matrix for the transformation T when our basis is B1, comma B2. Oh, and I forgot to note the columns of A are eigenvectors of A, and let's call them B1, comma B2. Okay, so that's the B1 and B2 I'm referring to. If those columns are our basis, then D is the B matrix for T. All right, what is the significance of that? Okay, that's the work. That's the work. The significance is what's more important. The mapping x to A times x and u, so some vector u, to d times u, du, describe the same linear transformation. The same linear transformation. Relative to two different bases. Two different bases. Okay, so in this small case, it might not seem like that big of a deal, but if A were some giant 500 by 500 matrix, and I wanted x to A times x, well, wouldn't it be much more efficient to multiply by a diagonal matrix if I can diagonalize that matrix? I mean, it would save time, it would save computing power, absolutely. So that's the significance here. There is another small topic and example brief at the end of section 5.4. I'm going to choose to skip them. You will not be held accountable for either of those two sections. Thank you for listening. Please start working on some homework. Email me if you have questions, especially about that notation, especially about example 2. That would be the one to really focus on in this section. Let me know if you have questions. Thank you for listening.